Thank you so much. I'm going to open by saying that I am a huge, huge fan of physics history. I am well acquainted with this famous room, and I'm completely intimidated and unworthy. But we are all here for the same reason, because we love science, and I'm especially honored that I get to give the first ever joint talk with my own husband, Sean Carroll. So this is also, this is the kind of thing we talk about at home, and it's the first time we've actually both talked about this topic. So you're kind of in for a first. Ultimately, this is a story about Alice and Bob. Alice and Bob, for those of you who don't know, are kind of fixtures when it comes to thought experiments, particularly those involving information theory, cryptography, and especially quantum information and cryptography. It just seemed a little more fun to play around with the idea of these actual two characters, Bob and Alice, and the different adventures that they get into. And the subject tonight, black hole firewalls, is another kind of thought experiment that physicists started playing around with, around the question of what happens when that daredevil Alice, who's the more risk-taking of the two, jumps into a black hole, while Bob kind of stays behind. Now, there's been a traditional way of thinking about this, sort of standard textbook, popular science, physics stuff for decades, that we thought we knew pretty well what happened, that she would be ripped to shreds by the powerful gravity at the singularity, that point of infinite density at the black hole's center. But when the physicists started playing around in the summer of 2012 with some of the big ideas, one of the other thought experiments that deals with information loss, they actually discovered a paradox. They discovered that it was possible that rather than being ripped to shreds by gravity, Alice might be burned up alive in this enormous wall of radiation just at the event horizon. She'd never even get the chance to be ripped apart to shreds. And so this talk is about that. And we're going to start off easy and slow, but it's going to get kind of mind-bending towards the end. The good news is you have Sean Carroll doing the really mind-bending stuff, and he's a tremendous communicator. So a paradox, for those of you who want a definition. A statement that apparently contradicts itself and yet might be true. In physics, they're quite commonly used. It's maybe not that specific definition. It's more that they're revealed by thought experiments, and they're used to illuminate certain counterintuitive truths, to reveal flaws in the assumptions or in the logic behind some of the reasoning in physics. So there's a long tradition of this. It goes all the way back to Zeno's paradoxes, including Achilles and the tortoise, how the fleet Achilles, can give the tortoise a head start, and although the Achilles can run so much faster, he never quite catches up. It became a foundation of calculus, figuring out what the limit was in calculus. Maxwell's demon was used to, illuminate thoughts on entropy and thermodynamics. In special relativity, Einstein came up with a twin paradox. What happens when one twin stays behind on Earth and the other two zips off into space at the speed of light? When that twin comes back, he will be much younger than the twin he left behind. That's a paradox, and it illuminates certain factors of special relativity. Tonight, we're going to focus on a lot of the quantum mechanical paradoxes. Sean will be telling you about the Schrodinger's cat paradox. He'll be mentioning Heisenberg's uncertainty principle. And central to this entire thing is the black hole information paradox. It is, in fact, the thing out of which Firewall's paradox came. But first, a little bit on the history of black holes. And I like to do this because, as I said, I love physics history. And I also love this guy, John Michell. He was basically an English rector in the 18th century. Common descriptions of him at the time basically say that he was short, swarthy, and fat. But he was known as a brilliant thinker. And in fact, he was far more brilliant than his contemporaries realized, because he was literally 150 years ahead of his time. He was trying to figure out one day how you could calculate the mass of a star. And he came up with this method, thinking that he could basically measure the reduction in the speed of light that was being emitted by it. And his thinking was very Newtonian. Remember, at this point in time, the debate over whether light was a particle or wave was still going on. And he very much ascribed to Newton's notion that light was a particle, or a corpuscle, as I think Newton called them. So he thought that gravity would slow down the light, and he could basically measure how much the light was slowing down, and he could use that to calculate the mass through a series of calculations. But he also had another insight. When he actually started doing the math, he realized that at some point, gravity would become so strong that the escape velocity would exceed the speed of light. The escape velocity is what happens, say, when you fire a cannon. And it was a famous thought experiment by Newton to describe gravity, how objects orbit. They're basically in free fall. If you escape the Earth's atmosphere and you go into near-Earth orbit, an object, the space station satellites, are just constantly in free fall around the Earth. But you need to be able to get beyond that. You need to be able to escape that part. So what happens if light can't escape? Then we wouldn't even be able to see the star. So he called it a dark star. And he also had another key insight. He thought, well, maybe you couldn't see it directly, but, well, it might have like a twin star near it that was bright. And you could look at that star and kind of figure out that there was a dark star next to it. Now, he was actually wrong about how to calculate the mass of a star, because as we now know, the speed of light is constant. That's thanks to Einstein. So there's no way you could have used that to calculate the mass of the star. But he was absolutely right about dark stars. Now, unfortunately, he died in complete obscurity. Nobody took him seriously. They thought he was crazy. This was so ahead of anything anyone had ever thought about that they thought there was no way it could possibly be right. He was not the only one, however. Pierre-Simon Laplace actually came to a similar conclusion a few years later, and he talked about it in his book, Exposition du système du monde, where he basically concluded it is possible that the greatest luminous bodies in the universe are on this account invisible. And again, he also was right. So it would basically take another 100 years or over 100 years before we finally had Albert Einstein re-envisioning space-time. In Newtonian days, remember, they kind of thought of space as a sort of three-dimensional or sort of Euclidean geometry space, and it was static. It didn't move. Einstein kind of re-envisioned it. There were 3 dimensions of space and the 4th of time, and they kind of combined to do space-time, and it became dynamic. It could twist and warp, and the things that did the warping and twisting were the massive objects in space, and that is where gravity comes from. Gravity is less a force and more, say, objects in light following the curvature of space. It was revolutionary. I don't think I need to tell any of you that. It changed everything. And among the lives it changed was a physicist named Carl Schwarzschild. He was, at the age of 40, he enlisted to fight in World War I, even though he was much older than some of the men out there. And it was, as you might imagine, a dreadful time in the trenches, dodging bullets and, bombs and bayonets and the whole bit. And one of the ways that he escaped the horror of the war was to do physics. And he came upon Einstein's theory of general relativity. A general theory of relativity. And he became fascinated. So in his spare time, he actually started working some of the equations. And he was basically trying to do similar something what Newton did. Newton would measure, say, the distance between the center of mass of an object and another point in space. And as you got closer and closer and closer, eventually you'd get down to a point. And Schwarzschild was trying to calculate the curvature of space. He hit a roadblock too, but it was well below zero. He basically hit a point where the equations just blew up, and nobody knew why. They didn't know what that point was. Today, I think we would call it the event horizon of a black hole. What we think now is that there might be something beyond that point, even though the equations, stop at that point. So the good news is, John Wheeler dubbed these objects black holes in 1968, and shortly after that, we found compelling evidence that, in fact, they do exist. The object they discovered that could be a candidate black hole was this X-ray binary star, Cygnus X1. They found it, or they determined in 1971 that there was no way it could be a neutron star. It was far too dense, and it was probably going to be a black hole. And you'll note it is a binary star system, so Michell was absolutely right. They could tell the black hole was there based on its companion star and its behavior. And this lovely animation here is based on actual data. Sean found it on the internet. It's a beautiful place, the internet. This is the black hole at the center of our Milky Way galaxy. And what they've done is basically, extrapolate, well advancing through time into the future to look at how the presence of that black hole affects the movement of bodies around it. So black holes, they're real, they're out there, they're probably at the center of most galaxies. So now we get back to Alice, because really this is all about Alice. Bob is kind of a, smaller player on the side there. So Black holes have some very interesting properties, and we know that they basically, have immense gravity, but what happens when she crosses the event horizon? The event horizon is what Schwarzschild unknowingly discovered. It's basically the point of no return. Once you cross that point, you're done. You're not getting back. No light can escape, no information or anything can get out of that. So Alice doesn't know it because she's not going to notice anything unusual as she crosses it, but she's pretty much doomed at that point. She just might not know it for a bit. Why is she doomed? Well, it's something that physicists like to call no drama, and it's based on Einstein's equivalence principle, this notion that gravity and acceleration are essentially the same thing. And what that means is an object in free fall, and Alice is in free fall, does not feel the effects of gravity. So she's not going to notice any extreme effect. She's just going to be floating along, kind of thinking space is the same as it's always been. Until. But first, that's from her perspective. Remember that we're talking about relativity, which means frames of reference are very, very important. Bob watches her slightly from a distance jump into the black hole, but what he sees is a little different. He sees her getting slower and slower because time slows down. Time dilates the closer you get to a black hole because of the extreme effects of gravity. So as she approaches the event horizon, she will seem to be moving slower and slower, and right at the edge, she's just going to seem to be frozen in space to him. And that's where time ends for him, as far as Alice is concerned, and he doesn't really know what happens beyond that point. For Alice, it's bad news, because there's an evil singularity lurking there at the center. She drifts along, and she drifts along, she's in free fall, and after a while, she starts to notice kind of an uncomfortable tugging, that she's being stretched. And that's because she's falling feet first towards a singularity. At this point, there's really only one way she can go, and it's towards her doom, towards the singularity. It's just sort of like that's the only way she can travel. And so the gravity on her feet becomes stronger and stronger, and it becomes much, much stronger than the gravity on her head. So it keeps pulling, and she gets longer and longer until she's basically, I think Kip Thorne called it being spaghettified. And finally, when she gets close enough to the singularity, she's just ripped to shreds. And there's nothing left of poor Alice. And again, poor Bob never knows the horror that awaited, his partner. Of course, this is not the end of the story. This is the classical view of a black hole according to Einstein's relativity. Things get really complicated with quantum mechanics, and quantum mechanics actually is relevant here because there's two different rule books for different size scales when it comes to physics. General relativity governs like the macro scale, the very large, the movement of the planets, things like that, everyday physics. Quantum mechanics governs the world of subatomic particles and the very small. Those of you who are familiar with the discovery of the Higgs boson will know that that was the last piece in what's known as the standard model of particle physics. So that model is now complete, except for one bit. That model does not include gravity. Gravity and quantum mechanics just don't play well together, and physicists have yet to devise a quantum theory of gravity that works. Black holes, because they basically are where relativity and quantum mechanics meet, and that's why they're so tremendously interesting to physicists. So surprise, this is something that we find out when we start applying quantum mechanics to black holes. Stephen Hawking, playing around with this in the 1970s, came up with the idea of Hawking radiation. Turns out that black holes are not completely black. And that's partly because space, empty space, when you're talking quantum mechanically, is not really empty. Space-time is really kind of you've got these virtual particles that are popping in and out of existence, antimatter and matter, Alice and Bob. And what happens when they meet is they annihilate into energy almost instantaneously, so they don't violate conservation of energy, they're not around long enough. But nonetheless, space-time at the quantum level is this kind of bubbly, frothy foam, so to speak. So what happens when these virtual particle pairs, Alice and Bob, kind of pop up into existence right at the event horizon of the black hole, and Alice is just a little bit closer to it, and she falls in, and Bob doesn't? What happens? What happens is you see the other particle, Bob, she basically disappears, and it seems as if Bob is light being emitted as radiation from the black hole, and the black hole will lose mass as a result. So black holes not only emit this very faint Hawking radiation, but they evaporate over time. And a physicist named Don Page, who's a very charming man, he's one of these people that just loves counting things, and one of the things that he counted was essentially what amounts to the half-life of a black hole. That point at which the black hole has radiated away exactly half its mass is called the page time. It's kind of like the midlife crisis for a black hole, and it is relevant to the firewalls debate. So Hawking radiation has some very troubling implications when it comes to information theory, and specifically what happens to information that falls into a black hole. This is where we get to the information paradox. Sean is going to talk about this a little more in depth as it pertains to firewalls. I'm just going to give you a brief overview now. It's very simple. We know that nothing can escape a black hole, so any information that it falls into it, that say that Alice carries with her into it, should be lost. There's a problem, though, because there's a key precept of quantum mechanics that says that information must be conserved. It cannot be lost. And Stephen Hawking decided that this was wrong. And he put forth this very radical notion that information was lost. I think his famous quote is, "Not only does God play dice, but sometimes he confuses us by throwing them where they can't be seen." Kip Thorne, one of his colleagues, agreed with him. John Preskill, another physicist, did not. And they made a very, very famous bet in the 1990s where Hawking and Thorne basically said information is destroyed. They said, okay, technically you could say it gets radiated out in the Hawking radiation, but it's so scrambled that when the black hole finally evaporates completely, there's just no way we could retrieve that information. Basically, you're throwing a book into a bonfire and it gets burned up into complete ashes, and then the ashes disintegrate, and then there's nothing left. So what do? That information is gone. Preskill just didn't like this, so he basically took the opposite side of the bet. He said that information could be recovered in principle, but he felt that physicists would need to devise a theory of quantum gravity to really understand the mechanism by which this could occur. Now, we don't have a theory of quantum gravity yet, as I mentioned, but Hawking did, in fact, concede the bet in July 2004. This was actually based on some work by string theorists, again, something Sean will talk about more in depth, but it's called the holographic principle. They basically found a cheat. And the cheat is, as long as that Alice and Bob can see two different things or have their own little bits of information, as long as they don't communicate with each other, it's okay. And also that the information gets encoded not necessarily in the black hole itself, but along the event horizon. So it's a question of volume, so 3D becomes 2D. And that is a little trick that they use mathematically to show that it was possible for information to be conserved. So what happened was Hawking presented Preskill with an 8th edition of Total Baseball, the ultimate baseball encyclopedia, from which information can be retrieved at will. And it was a big deal. Preskill was very happy. But Kip Thorne refused to concede. He basically said, there's more to the story. I don't think we have it. And it turns out that Thorne may have been correct not to concede, because today we have a new paradox, and that is black hole firewalls. This is something, again, a paper that Joel Polchinski, a string theorist in Santa Barbara, and Don Merolf and a couple of their students came up with in the summer of 2012. They were playing around with the information paradox, and Joe decided that he was going to try a little fun thought experiment, kind of run Hawking's thought experiment or thought processes backwards, just as a way to kind of double check and make sure his logic was good. And what he discovered was there was an anomaly. It's basically a logic problem. The physicist Raphael Busso calls it the menu from hell. What it basically says is there are 3 fundamental precepts that physicists know and love and hold dear. And what Polchinski et al. Found was that all of those 3 things cannot all be true. They simply can't. You've got to pick one to give up. One of those is what we've already talked about. It's no drama. It's the equivalence principle, the fact that Alice notices nothing unusual as she crosses the event horizon. We would really like to hang on to that for reasons, again, which you'll hear more of. The second one is we want information to be conserved. We really want it to be conserved. It's a fundamental principle of quantum mechanics, and if that's wrong, all hell breaks loose in quantum mechanics. And the third thing is locality, which is a little harder to describe, but essentially, if you picture you're dropping a pebble in a pond and it starts to ripple and then it ripples outward. The basic activity of dropping the pebble happens locally. It doesn't happen everywhere at once, and then it spreads out, and that's locality. And locality is actually one of the foundations of physics. It's really, really central, so central that it's hard to think of certainly classical physics without it. So which one has to go? Nobody wants to give away any of these, and I actually had the privilege of going to a Stanford workshop shortly after the Firewalls paper was published, the first Firewalls paper, and watching them fight it out. And it was fascinating to watch because nobody knew the answer. They still don't. They're still arguing about it. But the most obvious, easiest solution to it is to get rid of no drama. And when you sacrifice no drama, you get a firewall, a wall of radiation at the event horizon, and poor Alice gets burned alive. I personally would like to save poor Alice. I don't know how we're going to do that. I am hoping that my husband, Sean Carroll, can come up here and take you through the next stage of the talk, and hopefully he can find a way to save Alice.
Yes, we'll see what we can do. The answer is no, we will not be able to save Alice. This is not, sometimes I go around giving talks about the discovery of the Higgs boson, and it's a wonderful privilege to do that because there is a climax. We discovered the Higgs boson. It's a triumphant event. There will be no climactic triumphal event at this talk. This is going to say, hey, look, here's a puzzle. I don't know what the answer is. Maybe someone in the audience can help us out. So it all comes, as Jennifer said, from taking the idea of a black hole, which is well established, and which we understand in the context of classical mechanics, and applying quantum mechanics to it. So classical mechanics is what was handed down to us from Newton through Maxwell and Einstein. It's the idea that you have a state of affairs in the universe, and it evolves predictably through time. And also, what you see is what there is. In classical mechanics, there just is something, and you can observe it. In quantum mechanics, that's not quite the case. So here is your 1-minute introduction to quantum mechanics. What you can observe is much less than what actually exists. That's really the essence of quantum mechanics and why it is difficult to understand. Because nobody likes this. Nobody likes the fact that some fundamental deep facet of physics is being expressed in terms of what human beings can observe. That can't be right. And this is called the measurement problem of quantum mechanics. Surely we don't understand quantum mechanics well enough if we are reduced to making statements like this. And it turns out that we actually do understand quantum mechanics better than we used to. We know a little bit more about what qualifies as an observer and a measurement. We still don't know everything. We still don't have a complete picture that everyone agrees on the basic quantum mechanical reality. But we know how it works in practice. And how it works is there's certain kinds of observations that you can make, and they return results that we can predict the probability of getting a result. But when you're not making those observations, when you're not looking at the system, all of the different possibilities can simultaneously be there. So here's the classic example. Jennifer mentioned Schrödinger's cat, one in a long line of experiments that are among the most violent thought experiments that physicists like to talk about, where we kill small, helpless animals. In this case, well, we kill half of the animal. We kill the animal in some branch of the wave function of the universe. In this case, you have a cat. It's in a box. And what you want to do is you want to take advantage of the fact that in quantum mechanics, systems can be in superpositions of different classical possibilities. So in the box, you hook up a Geiger counter to a radioactive source, a hammer that can fall and break a vial that is filled with poison gas. So it has to be a Geiger counter or something else that is sensitive to a quantum mechanical event, like the decay of an atom. So there's something fundamentally quantum mechanical. It happens with a certain probability, and you wait until that probability adds up to 50%. And then according to the rules of quantum mechanics, Schrödinger points out that in this box, there is no such thing as an alive cat or a dead cat. In this box, the reality of the situation is there is a superposition of an alive cat and a dead cat. We're used to, in classical mechanics, having boxes, then we don't know what's in there. And you might say, well, there's a 50-50 chance the cat is alive or dead. But in that way of talking, there is a reality. We just don't know what it is. It's a matter of our ignorance. In quantum mechanics, it's not just a matter of our ignorance. The truth of what's inside the box is that it is both an alive cat and a dead cat, a superposition of both possibilities. And again, these days we know more about quantum mechanics than even Schrödinger did. So we know that You don't need to open the box to create either the alive cat or the dead cat. There's an effective observation being made all the time by the air in the box, by the light in the box, by the cat walking around and so forth. So long before you open the box, the split has already happened. But the classic explanation of this thought experiment is that before you open the box, there's a superposition of a live cat and dead cat. When you open it and observe, you only ever see either the cat alive or the cat dead. You never see a superposition of both possibilities, even though that's what quantum mechanics says is there when you're not looking. And that's the fundamental mystery of quantum mechanics, that when you're not looking at something, it's in a superposition of all these different possibilities. Now that leads to something that is very important for our firewall story, something called entanglement. This is not a picture of entanglement. This is just an excuse to put up a cute cat on the slide. Entanglement is the idea that in quantum mechanics, the way that we describe the world is not piece by piece. It's all at once. So in classical mechanics, let's say you have two boxes and you can't see inside, and you have a red ball and a blue ball, and you know that there's one of each, and each one is inside a box, but you don't know which one is in which box. Then you would say there are two possibilities. Either the blue ball is in box 1, the red one is in box 2, or the red one is in box 1 and the blue one is in box 2. One of those possibilities is true in classical mechanics, whether or not you know it. In quantum mechanics, inside the box you can have any superposition of maybe it's a red ball, maybe it's a blue ball. So in quantum mechanics, there can be entanglement. Not only can it be true that in one box there's a certain chance that the ball is red and a certain chance the ball is blue, but it can be the case that in the other box, whichever option is real depends on what's going on in the first box. So if you open just one box, it might be 50-50, the ball is red, the ball is blue. If you open the other box, likewise, 50-50, red versus blue. But if you open the first box and the ball is red, then you know with 100% certainty that in the other box it's blue. That is quantum entanglement. And if you want to be a little bit of a more respectable particle physicist, you can think of particles spinning or moving in certain directions rather than balls being red or blue. But it's the same overall point that quantum mechanics does not say there is a state of this box and a state of this box. It says there's a state of the world. And in this case, the world is either red over here and blue over there, or blue over there and red over there. So this little picture is supposed to show not two balls in each box, but the ball is in a superposition of red or blue that is entangled between those two boxes. This is another mystery of quantum mechanics. Forget about the measurement stuff. The fact that things that are separated from each other can nevertheless be entangled with each other bugs us also. It certainly bugged Einstein. He wrote a paper in 1935 with his friends Podolsky and Rosen. It came up with one of these paradoxes that Jennifer mentioned. The paradox, the EPR paradox, Einstein, Podolsky, and Rosen, says, look, this entanglement between two different particles, let's say a particle spinning clockwise and a particle spinning counterclockwise or something like that, or a ball being red or blue, so you have one particle over here that's in one state, another particle in another state, and they're entangled with each other. And that entanglement can persist no matter how far apart the particles are. So you can have one particle that is entangled with the other even though they're separated by hundreds of thousands of light years. They're on separate sides of the galaxy. This is not a picture of our galaxy, by the way. We don't have any pictures of our galaxy. This is the Andromeda galaxy. But this principle is the same. And in fact, we have done experiments like this, where the two particles are entangled, they're separated by kilometers. They're not separated by hundreds of thousands of light years, but still kilometers is pretty good. And according to the rules of quantum mechanics, if you observe this one and see that the ball is blue, you instantly know that the ball on the other side of the galaxy is red. So this bugs us because it was Einstein who pointed out nothing can travel faster than the speed of light. But the reality of which ball is in the box seems to be changing instantaneously all over the universe. And that bothers us a great deal. However, it turns out that this kind of instantaneous change is relatively harmless. you can't use it to talk to anybody on the other side of the galaxy. If you think about it, your friend over here, what do they know before you open the box? They know that if they open their box, the ball could be red or the ball could be blue. So you open your box and you find that the ball is red. You know that when they open the box, it's going to be blue with 100% probability. But they don't know that. They open the box and it's blue, and they go, well, that was one of the chances. No information has traveled. You cannot send a telegram using this kind of entanglement. So quantum mechanics manages to be non-local in a very subtle way. It bugged Einstein, but again, all he could do is say, look, this sounds weird, and the rest of the community said, yes, that does sound weird, but it's true. We will do the experiment, and it's true. This is actually how nature works. And the reason I'm going to such a great length here talking about this is because the particles that are emitted by black holes are entangled in a very, very specific way. So Jennifer showed you some nice pictures of black holes at one moment in time, a black hole sitting there in space, just a black sphere with fun radiation and people falling onto it. I am the hardcore quantitative science, so I drew a little picture in PowerPoint, and this is a space-time diagram of a black hole. So the hole itself, the two-dimensional surface enclosing a three-dimensional volume, is here portrayed as just a one-dimensional circle enclosing this two-dimensional disk. So this circle is the black hole at one moment in time, and the vertical axis is time evolving. The black hole is just sitting there, so nothing is actually happening in this picture, but we're going to make it a little bit more active in just a second. And inside, you see the singularity, and the event horizon defines the boundary of the black hole. For those of you who have been reading ahead outside of class, you will know that outside the event horizon, time goes vertically, but inside, time heads into the singularity. Once you're inside the event horizon, moving toward the singularity is precisely the same as moving forward in time. You can no more avoid hitting the singularity than you can avoid hitting tomorrow. That is why the singularity is so inevitable. Now what Stephen Hawking said is, out of this classical black hole will come radiation. And one way to think about that is, near the event horizon, according to the no-drama principle, the principle of equivalence that Jennifer talked about, you're in what physicists call the vacuum state. You're in empty space. There's nothing there. You could pass through the event horizon. You have a little detector looking for particles. You don't see anything special. There's no signpost, no escape after you reach this point or anything like that. But it's an empty space that obeys the rules of quantum mechanics. And in quantum mechanics, even empty space is kind of interesting. Empty space is actually a superposition of different ways that particles could be coming in and out of existence. Now, here in this room, space is empty and space-time is fairly flat. The gravitational field is not that strong. So if you look at empty space, you truly don't see anything. But in the vicinity of a black hole, what Hawking points out is that the gravitational field of the black hole can tear apart these virtual particles that are sitting in the quantum vacuum. So you can have one particle, Alice, falling into the black hole, and another particle, Bob, escaping to infinity. So what was two particles sitting there quietly in empty space becomes two real, actual particles. And that's very important. This one particle that goes out is what we call the Hawking radiation. That's what we see evaporating away from the black hole. So it's important that whenever you make one Hawking particle that escapes the black hole, secretly, even though you don't see it from out here, there is another particle that you also made that falls into the black hole. And given all of the setup, you will not be surprised to hear these two particles are entangled with each other. And that makes sense because these two particles are created essentially out of nothing, out of empty space. Empty space does not have any electric charge, it does not have any spin, it does not have any energy. It's empty space. But you've made particles out of it. And therefore, the two particles that you pulled out of empty space need to be equal but also opposite. If one of them has a positive electric charge, the other one has a negative electric charge. If one of them is spinning clockwise, the other one is spinning counterclockwise. If one of them has a positive amount of energy, the other one has a negative amount of energy. And indeed, any particle that escapes to infinity, escapes to the outside world, has a positive amount of energy. And therefore, as far as the outside observer is concerned, Alice, the infalling particle, has a negative amount of energy. That's why the black holes eventually shrink and lose their mass, is because essentially inside the black hole you see a constant drizzle of negative energy particles decreasing the mass of the black hole. So these two particles, Alice and Bob, that are created by Hawking radiation are entangled with each other. If this one is spinning one way, this one is spinning the other way. Empty space separated into sets of particles will necessarily give you particles that are always entangled. That's a consequence of the no drama principle. However, we want more than that. We want the information out of which we made the black hole to eventually escape. Once the whole black hole has evaporated, we want to be able to know exactly what it was made of. So we know that you have two particles entangled, and we know that all of the particles coming out are supposed to tell us what went in the first place. But that's a puzzle, because Bob is entangled with Alice, and what that means is that some of Bob's information is being left behind in the black hole. When Bob leaves, Bob is entangled, and we're not exactly sure how, therefore the information is not yet getting out. What you say to yourself, if you're trying to make sense of this, if you're a physicist who believes that black holes evaporate but also believes that information is conserved, is that's okay, because later there's another particle named Carrie, and Bob will just be entangled with Carrie in exactly the same way that he was entangled with Alice. So if Bob is spinning clockwise, both Alice and Carrie are spinning counterclockwise, and vice versa. So maybe that's how the information gets out. This early radiation, Bob, is entangled with the late radiation, Carrie. And then, of course, Carrie herself, since she is a virtual particle that was torn out of the quantum vacuum, she'll also be entangled with Dave, but Dave is just not going to be important to our story. Sorry, Dave. Here is what we're trying to say. We're trying to say that Bob started life entangled with Alice and eventually is entangled with Carrie. That's the only way that information can get out of black holes if there is no drama near the event horizon. The problem is that cannot happen. Quantum entanglement does not work that way. Quantum entanglement does not let you mess around. Sorry. In fact, literally, the phrase that this goes by is the monogamy of entanglement. If you are a particle, Bob, and you are maximally entangled with another particle, Alice, there's Bob, you cannot possibly be entangled even a little bit with another particle called Carrie. The rules of quantum entanglement are more strict than the rules of free love in the 60s, where this was first discussed. So I got this slide, this picture from John Preskill, who Jennifer already mentioned, a colleague of mine at Caltech. And John got in trouble for showing this slide because it says at the top, monogamy is frustrating. As if poor Bob is frustrated because he's stuck in this relationship with Alice and he can't get together with Carrie. So John started changing the labels, and he made it Becky over here is entangled with Adam and cannot be entangled with Charlie. And then he got in trouble for that too, because people were saying, well, what are you saying about Becky's morals anyway? Becky's just sleeping around? Come on. So don't label your particles by people's names is the short lesson here that we should learn. But this is a big puzzle, and this is it. This is the puzzle that we are faced with. If you believe everything on the previous slide, we have shown logically that the fact that Hawking radiation comes from a region with no drama, flies through empty space, and eventually is going to bring all of its information back, can't happen. Not all of those things can all happen at the same time because entanglement is monogamous. Bob cannot be entangled with both Alice and Carrie. So something has to go. This is the AMPS argument. AMPS are Almeri, Marolf, Polchinski, and Sully, the Santa Barbarians who made this paper in 2012. And they went through the list. They went through the list that Jennifer mentioned from Raphael Busso. What could be going wrong? They're all kind of pretty dramatic. One possibility is that information really is lost. Maybe if you take encyclopedias and throw them into black holes, the information in those books is truly lost forever, not just in practice, but even in principle. That would be a dramatic violation of everything we think is true about quantum mechanics. And, in some sense, that's okay. Everything that we think is true about quantum mechanics was a dramatic violation of what we thought about classical mechanics, and yet it turns out to be right. It might be true that quantum mechanics is not the final theory of everything. In fact, Stephen Hawking, who was the first to propose that this was true, said very explicitly that he thought this was the right answer. This is why he made that bet that he eventually conceded and is now having second thoughts about conceding. But despite the fact that it's a logical possibility that information is lost, what you would really like to see is a well-defined theory of how information is lost, where it goes, under what circumstances it is destroyed and conserved, and so forth, and nobody has been able to do that. So no one's been able to come up with a consistent, coherent framework in which information really is lost. That's not to say it's not true. It's just that it's not one of those ideas that sort of falls into your lap and everything suddenly makes sense. It's an idea that is suggested and you think about it and it just becomes more and more puzzling as time goes on. Another possibility is locality. This is a somewhat subtle concept, but it's basically the idea that things that happen in the world happen at different locations in the world. So a particle doesn't just pop out of existence here and suddenly reappear over there. A particle propagates from here to there, obeying the laws of field theory, of quantum field theory in this case. So this photon, or the electron, or whatever it is that we've labeled Bob, moves from the event horizon very, very far away, following the laws of particle physics, which are local in space. Maybe that's not what happens. Maybe the information contained in Bob doesn't obey those laws. That would be very dramatic and interesting. Finally, there's the possibility that there is in fact drama at the event horizon, that this thought we've had since the 1960s that Alice could fall through the event horizon and never notice anything is just not right. That instead, there is a tremendous amount of high energy radiation that Alice sees when she gets there. If you think about it, this Hawking radiation, it comes to you, it's very faint, it's very cold, it's very long wavelength, but when you leave a black hole, a photon gets redshifted. It loses energy. It suffers what we call the gravitational redshift. So a photon out here that is very low energy, if you trace it back in time, was very high energy when it left. Usually we say, well, that's okay, it was high energy, but it was invisible because it was part of the quantum vacuum. And this idea is saying, actually, no. It was just there as a super duper high energy particle. And when Alice tries to cross the event horizon, she would be incinerated by this wall of fire, all of these high energy particles lurking near the event horizon. And in fact, if this were true, there wouldn't even be anything called inside the black hole. All of the stuff that we think of as making up the black hole would simply live on the horizon. And that would be a very dramatic difference from how we think about black holes ordinarily. Sadly, neither Almeri, Morel, Polchinski, or Sully seemed to know that the word firewall is used in computer science to be a good thing, to stop evil people from getting in where you want to go. They use that as a bad thing, something that burns you to bits as you fall into a black hole. So the smart money among people who are my personal friends is that locality is going to be the thing to go. This is a very dramatic thing, but it seems to be a little bit easier to live with than the other two going. So let me talk a little bit about locality. As Jennifer mentioned, you can visualize what locality is by thinking about what happens when you drop a pebble into a pond, or when you make a sound, or when you flash a light, or anything like that. The effects of what you do not show up all throughout the universe instantaneously. They move at a certain rate, the speed of light, or the speed of sound, or the speed of waves in the water. They move from one place to the next, to the next, to the next. That's a reflection of the fact that the way we talk about the world is by talking about what's happening at every point in space. So this is space, and if I want to tell you what's happening in some region of space, I tell you what's happening there, and what's happening there, and what's happening there, and so forth. If someone says, what's going on in this lecture hall, I could tell them the identity of every person and every seat in the lecture hall and what they are doing. Separate information at every point in space. Now, quantum mechanics complicates this a little bit because it says there can be separate superpositions of classical realities, but each one of those classical realities is local in space. It's a description of there are so many electrons over here, so many photons over there. Everything is defined by where it is in space, and that is the principle of locality. So entanglement makes the concept of locality a little bit more problematic, but it doesn't break it. It just makes it more interesting. The quantum state of these two particles that are very, very far away from each other is non-local, but the dynamics, how they actually change with time, how you can actually send a signal through space, is all perfectly local. Even with quantum mechanics and entanglement, if you want something to happen, you need to start it here and then it needs to travel through space to get anywhere else. So, despite the fact that locality is very precious to us, it's probably not right. In fact, other thought experiments involving black holes have already given us reasons to believe that when it comes to quantum gravity, which is what we're doing here after all, we're quantizing gravity itself, the fabric of space-time. When it comes to quantum gravity, locality is probably not an inviolable principle. The question is, how much violation of locality can we get away with? To what extent is the universe not really described by what's happening here plus what's happening there plus what's happening there? So we have two clues that have been given to us by thinking about black holes. One is called the holographic principle. And this actually goes back to Stephen Hawking once again and his radiation from black holes. One of the implications of Hawking's discovery that black holes radiate, by the way, I should, because I'm in a venerable lecture hall, stop and say, we have never seen a radiating black hole. This is not data that we were talking about here. I'm sure that black holes radiate. My confidence is very, very high, but I could be wrong about that. It's cherished rules of physics that tell us that black holes radiate, but it sure would be nice to have some experiments or some data that said the same thing. All right. Sop to the experimentalist now complete. Now we can go back to crazy theorist land. So Hawking showed that a black hole actually has a lot of entropy. Entropy is a way of talking about the disorderliness, the chaoticness of an arrangement of stuff in the universe. When cream and coffee are all mixed together, they're high entropy. When they're separated, they're low entropy. So ordinarily, if you want to actually quantify the amount of entropy of, let's say, the air in this room, you just talk about the number of ways you can rearrange the molecules that make up the air in this room. And the number of ways you can rearrange the molecules just depends on the volume of space that we have in the room. So it is an absolute rock-solid feature of entropy in the ordinary experimental macroscopic world that entropy scales like the volume of the system you're looking at. If you double the volume, you will double the available entropy. What Hawking showed is that for a black hole, the entropy of a black hole scales as the area of its event horizon. So a black hole has a volume. There's a volume inside the event horizon. There's a three-dimensional volume enclosed by the event horizon. You might have guessed that the entropy of the black hole is proportional to that volume inside. That is not right. It is proportional to the area, some two-dimensional quantity, the area of the event horizon, not the three-dimensional quantity, the volume inside. People know that, have known that for a long time. It didn't really sink in seriously until the 1990s, when Gerard de Tufte and Leonard Susskind and others promoted this idea to not just a weird idiosyncrasy of black holes, but a fundamental feature of nature. They proposed the holographic principle that says that basically any time you think you have a three-dimensional collection of stuff, like us here in this room, all of the information needed to describe us can be compressed into one two-dimensional surface. In a black hole, it becomes frighteningly real. In a black hole, the two-dimensional event horizon really does contain all the information you need to talk about what's happening inside, according to the holographic principle. But it should be true even in this room or the galaxy or the universe. And if that's true, locality is being dramatically violated, because there's a lot less that can possibly happen in this room than you thought could. You thought something could be happening here and something could be happening there, and different things could be happening at every point. But the holographic principle says, no, that's not true. And one of the arguments for it is that if you imagine all the different possible things that could happen, most of them would have a lot of energy and the room would collapse to make a black hole. So there's an upper limit on the number of things that could happen in this room, and the size of the upper limit is proportional to the area of the walls around this room. So there's this hypothesis that all of physics really lives in a world that is one dimension lower than the world we actually see. And again, we're trying to make sense of this idea, and we're making progress, but we're not completely there yet. The other idea that has come out of black holes and argues against locality is called black hole complementarity. Remember, I said that from the point of view of Bob far away, he sees radiation coming out of the black hole, and he says, well, if I trace it backward, it must have been very, very high energy radiation when it left the event horizon. Whereas Alice, in the conventional way of thinking about things, passes through the event horizon and sees nothing there, just empty space. So they have incompatible ways of describing the same situation. Bob thinks the event horizon is bubbling with high energy radiation. Alice says there's nothing there. Black hole complementarity says they are both correct. Black hole complementarity says there are different sounding ways of giving equivalent descriptions of the same fundamental underlying reality. And that two things that are seen by two observers can look very, very different as long as the observers can never get together to compare notes. So what happens is, if you give Bob enough time to collect the Hawking radiation and figure out what he thinks the horizon looks like, and you give Alice enough time to fall into the horizon, if Bob then says, all right, I've got some data, I know it's coming out of the black hole, I'm going to fly into the black hole and tell Alice what I saw, it is too late. She has been spaghettified and crushed into the singularity. So these two observers see a very different thing happening in the world, but they can never talk about it. Only we godlike physicists, looking at the whole thing from afar, can give the bird's eye view of everything that is going on. That is the principle of black hole complementarity. It's borrowed from the early days of quantum mechanics, when Niels Bohr pointed out, you're allowed to measure position or you're allowed to measure velocity. You're not allowed to measure both at the same time. That was quantum complementarity. This is black hole complementarity. So again, it's a violation of locality in some sense. It says that the right way to describe the world isn't what's happening here and what's happening there and what's happening there and what's happening there separately. What's happening right there can depend in a very dramatic way on who's looking at it and from what perspective. So somehow, all the information about what's going on in the world is not simply located at individual points in space. It's encoded in some cryptic way that we don't yet understand, and that's what we're trying to get at by doing these thought experiments. The problem is, these two types of non-locality don't seem to be enough to solve the firewall puzzle. Remember, in the holographic principle, you say, okay, all the information is there on the horizon, but that doesn't tell you anything at all about what you see when you fall into the horizon. And in complementarity, you explicitly say that Alice, when she falls in, doesn't see anything at the horizon, but it's just an assertion. You're not explaining how the entanglements can actually work. So the force of the black hole firewall paradox is that the amount of non-locality you seem to need to make physics work is even worse than that given to us by the holographic principle or complementarity. So what could be going on? And again, nobody knows what's going on, so I will tell you two crazy sounding ideas. The hope is that they're just crazy enough to be right. One idea is that there really isn't any such thing as inside the black hole. This idea is that what you think of as inside the black hole is just a copy of certain things going on outside the black hole. And this is a little bit strange to get straight, because in fact in quantum mechanics there's a rule that says you can't copy things. There's what is playfully called the no Xerox theorem or the no cloning theorem. If you have a quantum bit of information, you can move it and you can evolve it and so forth, but you can't just copy it without destroying it. But this is saying something more profound than that. It's not that you fall in and there's a copy of you that goes in and a copy of you that goes out. It's saying that the interior of the black hole really is exactly the same thing as the exterior, secretly. It's secretly encoded in some weird way. So the difference is that if I could take a quantum mechanical object and clone it, then I could separately do things to this one and then do separate things to this one. But this is saying that literally everything that happens inside the event horizon is mirrored in some exactly equivalent way by things going on outside the event horizon. That is a set of words that we can say. Those are all English sentences that are more or less grammatical. We don't really have a quantitative theory about how this would work. It would, in fact, solve the black hole firewall puzzle, because this thing that we thought was a photon falling in, labeled Alice, was exactly Bob all along, or one of the other photons. It seems dramatic, but it might actually be true. And then just to go one step weirder, we have what is playfully called ER equals EPR. This is an idea of, again, Lenny Susskind and Juan Maldacena. EPR, we already mentioned, Einstein, Podolsky, and Rosen are the ones who first took quantum entanglement and put it front and center. ER was just Einstein and Rosen. Podolsky didn't get involved, but it was a paper written, I think, the same year as the EPR paper about a totally different subject. About the idea that, given general relativity, given the idea that space can be curved and dynamical, you could imagine building little bridges in space-time that we call wormholes. So Einstein and Rosen, what we call an Einstein-Rosen bridge, is just a connection between two widely separated pieces of universe, maybe that look like black holes from the outside. And the trick here is that you think that the distance between this black hole and this black hole is very large if you traveled this way, but secretly it can be very short if you take the shortcut through the wormhole. This was the Einstein-Rosen suggestion, and it was a little bit speculative, but it went into the toolbox of theoretical physicists, and it had nothing to do with entanglement or quantum mechanics. And Maldacena and Susskind are saying, well, actually, maybe it does. Maybe when two particles are quantum entangled, secretly there is effectively a little tiny wormhole that is connecting them. That for certain purposes, you can think of quantum entanglement as being enforced by a little bridge in space-time that brings those two particles together. So the way that the information can get out of a black hole in this idea is that the black hole is connected by little virtual wormholes to all the particles that are being emitted as Hawking radiation. And really, the importance of this suggestion is that space-time is not fundamental. Space-time is an approximation that comes out of thinking about quantum states and how they are entangled with each other. We live in space-time. We tend to think that space and time are kind of important. This point of view is saying, you know, they're just good ideas. They're nothing absolutely fundamental. They're just sort of a good approximation. And finally, of course, there is the other possibility that firewalls are real, that we've been wrong for the past 50 years when we're thinking about what happens when you fall into a black hole. It would not be painless until you got spaghettified. It would be painful long before then. This is the old picture of black holes. You would just fall in, nothing would happen. And maybe that's completely wrong. Maybe, in fact, there is a wall of ultra-high energy radiation that incinerates you to bits long before you fall into the event horizon and would be spaghettified. Again, that seems weird to us because the horizon in classical general relativity not only is nothing special going on there, but the gravitational field isn't even that strong. We think of, if you're right next to a black hole, the gravitational field better be pretty strong, but it's really just, it's so big that you don't notice. You would not be spaghettified at the event horizon. You're not spaghettified until you're well inside an astrophysically large black hole. So this idea is saying that in a region of space-time that should seem perfectly benign and happy, something really dramatic is going on. And that may be true, but if so, that would be a very, very important discovery. So to conclude, why is this important? Why does this matter? And we could have started by telling you why it matters, but you were already here, so we figured you'd go along. The point is that trying to quantize gravity is probably the most important outstanding puzzle in fundamental theoretical physics, the ultimate description that we have of how nature works at a deep level. We have a very, very good theory of particle physics, quantum mechanics, and space-time. The quantum mechanics part doesn't play well together with the space-time part, and that's the search for quantum gravity. But to get a theory of quantum gravity, we need to know what it is that we are quantizing. We think we understand classical gravity. Einstein told us what it is. It's the curvature of space-time. But all of these ideas from black holes, getting the information out, the holographic principle, complementarity, firewalls, all of them are telling us that space-time itself is not fundamental. That when we talk about space-time, it's like talking about the air in this room as some kind of fluid that has a temperature and a pressure and a velocity and a speed of sound and so forth. But we know, you and I know, that if you look closely enough at the air of this room, it's no longer a fluid. It resolves into different atoms and molecules. This kind of idea is saying that, sure, space-time is a nice approximate way to talk about the world, but when you really push it, it breaks down and needs to be replaced by something else. We have no idea what that something else is. That's the problem. If quantum gravity is not a theory of space-time curvature being quantized, it's a theory of something else being quantized, something that is related to the space-time that we observe every day in some mysterious, non-local way that we haven't fully understood. We have some provocative clues, we have some toy models that seem to give us useful information, but we're nowhere near the final answer yet. And that's what makes it fun. That is why this is a fun thing to think about. It is not going to cure cancer or build a better iPhone, thinking about the holographic principle and black hole firewalls. All it will help us do is understand at a deeper level what the fundamental nature of reality is. And I think that that is something that is well worth thinking about. Thank you. So now we have plenty of time for questions. I'm going to bring up my lovely wife again. We're told, I don't know if it's true, we were told that the last time a husband and wife team spoke at the Royal Institution, it was Marie and Pierre Curie. And they didn't let her talk. Come a long way. All right, way up, right in the middle. Whoops.
Thanks.
It's local.
I have a question about the human Alice and Bob, which is probably just a misunderstanding. But when Bob is watching Alice enter the black hole, she basically freezes in sort of space, and he doesn't actually see her. Well, an infinite amount of time would possibly pass before she enters the black hole. When I was young, I think there were still ideas of the big crunch, and I remember thinking about this, thinking Alice can never get to the singularity because time is basically slowed down so much from the point of view of Bob and the rest of the universe that the big crunch will happen before she ever gets there. Now, obviously, the big crunch may not happen because of dark energy, but as the black hole evaporates, would the evaporation of the black hole not sort of overtake Alice reaching the singularity? I don't know if that's really a question. It's really a request for elaboration.
Yeah. And the question is, don't you agree? Yes. But I do agree. Actually, you're completely right. Your younger self was not right, because in a black hole that would not have evaporated away, from Alice's point of view, the clock is still ticking, absolutely in a normal way, when she crosses the event horizon, and there's a finite number of seconds before she hits the singularity. If the black hole is one solar mass in size, between the event horizon and the singularity takes about 1/1,000,000th of a second, from her point of view. But now with the black hole evaporating, we honestly don't really have a very strict answer to that question. There's still going to be tremendous gravitational fields in there. You'll probably still be spaghettified, but there's probably not a singularity. That's probably an artifact of classical general relativity. So it's more like you all get mixed up and somehow your information comes out again.
Would the black hole not evaporate? I mean, from Bob's point of view, he's seeing the black hole evaporate sort of in external time. Alice is almost frozen from his point of view, so why isn't it that the black hole evaporates before anything happens to Alice? It seems to tie with your idea, the idea that it's the event horizon, which is this massive radiation. There's actually nothing inside.
Well, Alice's point of view is also valid. And in her point of view, she enters the event horizon. The point is that there is a tiny bit of exaggeration when we say that from Bob's point of view, Alice stops moving. If you see somebody, that means they are giving off radiation. That means that time is passing. So even though Bob sees Alice move more and more slowly, Alice also appears redder and redder and fainter, because she's embarrassed because she's falling into a black hole and because the photons are being redshifted. So Bob only gets a finite amount of information about what happens to Alice, and that information is not complete. The actual fact of Alice is that she enters the black hole.
Thank you. Is there any potential research aimed instrumentation that could give you any evidence of what you're talking about?
Don't you love the theory?
Yeah,
Pureness
the
of the
should
theory?
be enough. I think that the most we could possibly hope for is evidence of Hawking radiation. The evidence for like firewalls and crazy wormholes is a bit much to ask. If a black hole is big, like if you make it from a star or the center of the galaxy, the weird thing about black holes is the bigger they are, the fainter they are. The lower their temperature is. So for an astrophysically large black hole, it's actually a lot colder than the surrounding space. And the amount of Hawking radiation it's giving off is much fainter than anything else in the universe. The only hope is to find a really tiny black hole, a primordial microscopic black hole, and those could be exploding today. And it's possible that we're even observing them in terms of gamma ray bursts or something like that. It would just be very hard to tell whether or not you were actually observing an exploding black hole, and probably there aren't any. But that would be the biggest hope, to find something. And actually, Jennifer is an expert on the actual experiments in the lab for the Bill Unruh's black holes.
Oh, I'm not an expert is a strong word. Yes, they have small analogs that Bill Unruh is doing using, it's a little bit like water going down a drain. He's basically been able to create sonic analogs of black holes or with mechanical water waves where you actually do get a kind of trapped effect. Similar to light not being able to escape, suddenly sound can't escape. And he's had a lot of very interesting, hands-on experimental work with that. The math isn't exactly the same as for a black hole, but it's essentially what amounts to a toy model with some experimental evidence. So the hope there is that through these small-scale experiments, they can actually get some insights into the larger, full black hole equations.
Yes.
I have two questions. Both unrelated and related depending on your point of view. So first question is...
Complementarity.
Exactly. Normal black holes, supermassive, and these theoretical micro ones, are they different sized animals of the same species, at least from a behavioral perspective, or is it different species? First question. Second, in terms of Bob and Carol and Ted and Alice, as far as information transfer, is there 100% fidelity of the conservation of information, or is there noise in the system?
The first answer is they are certainly the same species. They're the same animal. In fact, black holes are arguably the simplest things in the universe. If you tell me what the mass of the black hole is, what its electric charge is, and how fast it's spinning, you have told me everything there is to know. It's not like a planet where you have to tell me the topography and what it's made of and all those things. Black holes are all very simple and basically identical to each other. The information loss, again, it's we think, an absolutely ironclad rule of physics that information is 100% super duper conserved. It's like being a little bit pregnant. A little bit of information loss is very noticeable. We could be wrong about that, but that is the thought. That is the idea that we're working under.
I think I would just add one thing, which is, black holes of different sizes actually radiate faster. If they're smaller, they disappear almost instantaneously. If they're larger, so the rate at which they evaporate is tied to their size, and I think that's the only difference. I mean, they're pretty much the same species, but they're at different size scales, and that does affect the rate at which they evaporate away.
Someone right here had a question.
Thanks, that was a wonderful lecture.
Thank you.
If going back to that holographic effect, if you and that door there, and there's no space, yeah, that one, and there's no space between you and the door, what would happen to the information of the air between you and the door?
Well, that's a very good question, but you have to understand exactly what's being said. If you think about a hologram, have you seen a hologram?
Yeah.
So it's a two-dimensional piece of film that you shine light on and a three-dimensional image appears. So the holographic principle is saying that this room is like that. So it's not saying that there's no air or no space in between me and the door. What it's saying is that all of the information needed to talk about the air in between me and the door is embedded in some secret, invisible, two-dimensional space. But it is all there. And there are fewer ways that there could be air between me and the door than you might have thought, because there's not as much room in the two-dimensional hologram to put them as there would be in a three-dimensional space.
Thanks.
This follows on actually from talking about this principle of a two-dimensional space in which three-dimensional information is encoded. I just wondered if you could talk about how this relates to the predictions of string theory, which predicts a lot more dimensions, I believe, and what we actually mean by dimensions in both senses.
That's on you.
Yeah, you would think that they would get their story straight and decide whether there are more or fewer dimensions than we thought there were. But it's actually quite compatible. In string theory, there are supposed to be extra dimensions of space, which are invisible to us for a completely different reason. Those dimensions are invisible to us because they're curled up into a little tiny ball, and we can't see them. They're much smaller than atoms. Or we are stuck on some three-dimensional surface inside some bigger space, and we just literally cannot get there. This is saying that all of those descriptions are ways of talking about curved space-time, but the right way to talk about the fundamental nature of curved space-time is just to go one dimension less. So however many dimensions there really are in the fundamental description of reality, curved space-time with gravity always appears like it has one dimension more. That seems to be the principle that holography works on. So it might be that the real number of dimensions of space-time is 8, and therefore gravity works in 9-dimensional space-time. That's one of the theories you can bat about, yeah.
Is there any suggestion that there's a link between quantum gravity and dark energy or dark matter?
Any question that begins, is there a suggestion? The answer is yes. People have suggested that. Dark matter is probably quite parochial and conventional by these terms. It's probably just another particle that we haven't found yet. People have tried more outlandish ideas. It's a modification of gravity, something holographic, something like that. Those ideas literally don't fit the data very well, whereas the idea that dark matter is just another particle seems to fit the data very well. Dark energy, which is more subtle, it's something that is smoothly distributed throughout the universe and makes the universe accelerate. We have less idea what the origin of that is. So it's absolutely possible that when we do, it'll in some way involve ideas like holography, but I really can't tell you precisely how. It's right there. Yeah.
Hi. You spoke earlier about how quantizing gravity was one of the greatest challenges in modern physics. Could you comment on how cosmic inflation helps explain that?
Don't think it does, is the short answer, but it might help us learn something about what works. So inflation is this idea that in the first very, very tiny fraction of a second after the Big Bang, the universe underwent a huge, fast amount of expansion that smoothed everything out and left us with the universe we see today. The models that we have of inflation are basically classical, are basically not involving quantum gravity. There's a little quantum field theory in there, but gravity is still classical in that regime. So you don't need quantum gravity to make inflation work, nor does inflation rely on quantum gravity in any way. However, if inflation is real and we can get observational evidence about it, it is a phenomenon that happens at an energy scale much closer to the energy scales of quantum gravity than any other phenomenon we have any way to observe in the universe today. So literally, the difference in energy between the temperature of the air in this room and the protons that you smash together at the LHC, the Large Hadron Collider, is less than the difference in energy between those Large Hadron Collider protons and the inflation energy. So if we can make that leap up to inflation, which maybe we have with recent data about the microwave background, that's as much of a leap forward in energy as all of the previous rest of the history of physics. This side, do we have any? Oh, good.
Hi, thanks again for the talk. It's fantastic. I wanted to ask, would you comment on what these paradoxes might mean for our understanding of cosmology in the sense of the origin of the universe and its future? In particular, I think I remember reading that holography may link what we think of eternal inflation and the many worlds interpretation of quantum mechanics that we think is completely different things. Somehow linked via holography, but I have no idea if I've got that right or how.
Yeah, you do actually have that right. So, complementarity. So the question is, what do these things have to do with cosmology? And it's interesting because as a cosmologist, my goal in choosing my career was to go into the simplest possible area of science, because the universe is actually very simple. You ignore all the details and just look at it on large scales. And yet, I went wrong because black holes are even simpler than the universe. So applying these ideas to cosmology is hard because the universe can do more things than a black hole can do. It's that question, black holes just can't do many different, there's just not that many possible black holes. Having said that, let's imagine taking complementarity very, very seriously. And complementarity says that the point of view of someone outside the horizon is different than someone inside the horizon. So because our universe is accelerating now, because there is dark energy, there's a different kind of horizon that we are inside. If distant galaxies move far enough away, they are accelerated away by the expansion of the universe, and we will never see them again. So they are outside a horizon. So certain ambitious physicists have said maybe there's a sort of complementarity that works for cosmological horizons as well as black hole horizons. And if that were true, what it would be saying is that the entire description of the universe is our observable universe plus our horizon. Everything outside is secretly embedded on our horizon. So you don't need to talk about the entire universe outside what we can see. It's all secretly encoded in this local bit, okay? And if that's true, then quantum mechanics says that the universe is like any other quantum mechanical system. It can be in a superposition of different possibilities. So this observable bit of universe can be in a superposition of different states of being, and that would be the cosmological multiverse. So the many worlds of quantum mechanics and the cosmological multiverse would be brought together in a happy relationship, and it's all completely speculative at this point. Where are we?
Is there one up there?
I haven't seen any up there, but there's a couple of plucky folks over here. Is there anyone up there? Yeah.
I just wanted to talk about dark energy and inflation. If you imagine a speedboat going across the water, and the speedboat itself is the inflation, the ripples behind it might be dark energy, because dark energy says that things that are furthest away from us are moving further away fastest, and those that are closest to us are moving away less quickly. So that would be the same thing with a speedboat, with the ripples coming out from a speedboat. As you get further away from the actual speedboat, the ripples themselves move slower. So are we looking for something that doesn't actually exist? It's just inflation.
So my personal point of view is that the speedboat analogy is probably not the best one. Because inflation is not the movement of something through something else. It is literally the size of the universe changing with time. And it is true that when we talk about acceleration of the universe and dark energy, distant galaxies are moving away from us faster than nearby galaxies. But that's only because the universe is expanding. That was still true even before we knew about dark energy or the acceleration of the universe. Edwin Hubble's famous law says that the apparent velocity of a galaxy is its distance times a constant called Hubble's constant. So as the distance gets bigger, the apparent velocity gets bigger and bigger. And that's really just explained by the fact that there's more and more space in between you and the distant thing. So it's a tricky thing because we very naturally fall back on analogies that relate what the universe is doing to things we're familiar with, all of which are things inside the universe doing things, subsets of the universe doing things. But in some ways, the universe is a unique kind of beast. So I think that the dark energy really needs to be some kind of energy. I don't think it's sort of automatic or anything like that. Sure.
There's one back there.
Thank you. I'm still having a little trouble understanding what you were saying when...
What? All right.
Back early on, with your Alice photon falling into the black hole and your Bob photon being emitted, why is it that Bob is emitted? Why can't he just sort of hang around outside the event horizon for a little while and then follow Alice in just a bit later? And sort of following on from that, I also don't quite see where this firewall comes from. Does that come from the same phenomenon as the original Hawking radiation, or is that just something else that would give us a similar prediction?
Yeah, so to the first question, why couldn't Bob just hang out? Have you ever tried just hanging out right next to the event horizon of a black hole? I think as Jennifer mentioned, most of the virtual particles near the event horizon do just stay there. You know, they get created and they get annihilated very quickly. They don't escape to infinity. So when we draw these pictures, we're just picking out the plucky ones that manage to escape. So most of the virtual particles are just sitting there near the horizon. And the important thing about those particles is that if the combination of the states of all those particles looks like empty space, it must be that all those particles are entangled with each other in a very intricate way, in a very intimate way, I should say. And the firewall paradox is just saying that if you want to get the information out from Bob and all the other particles coming on later, then it can't be true that Bob and Alice are entangled at the same time. If Bob was entangled with Alice, he's not entangled with anything else, and therefore the information is getting lost every time he leaves. But as soon as you disentangle Alice and Bob down there, it's no longer empty space. It's a wall of high energy particles. That's the firewall claim in a nutshell.
Thank you.
Finally, someone back there.
Yeah, sorry. Okay, so just another question relating vaguely to entanglement. And I'm sorry if this was covered in the lecture and I maybe dropped off and missed it. It was very interesting. That could be the beer that I had earlier. But so I think, so when you talk about entanglement, so in my mind, that is a way of you describing a supposition, which is a way of you saying that something you observe infers a truth about something else. So, for example, you observe the ball is blue, that implies that the other ball is red. Mm-hmm. But regardless of whether you observe one truth or another truth, both of those truths still exist, whether you observe them or not. So a ball is still blue and a ball is still red somewhere. So as soon as you observe whether one ball is blue or red or whatever, then that entanglement, in a way, does that cease to exist? Because you observed that one ball is red, the other ball becomes blue, they're entangled, but does that relationship maintain? So if you were able to change the ball you've observed to red, does the other ball become blue? Or does that entanglement cease on the point of observation, is kind of my question.
Yeah,
I don't know if that makes sense.
It is a perfectly good question, and there's two things. One is that, yes, the entanglement does persist. When you observe one box or one ball, the entanglement that was there stays there. So one way to be entangled is this ball is definitely red and this one is definitely blue. That's a kind of entanglement. More interestingly, there's a fraction of the superposition that is red and blue and the opposite that is blue and red over here. But the point is when you make an observation and make this one red, that one instantly becomes blue. They're still entangled, just in a more trivial way. And that is an experimental fact. That is not just a theory. We have done that experiment. We have put them in superpositions, moved them apart and observed them, and then checked. And it always works out exactly as we predicted.
So can you then sort of reboot the supposition with the same two particles?
Once you have observed the particle and you've seen that it's red or blue, it stays red or blue. So that is what is called collapse of the wave function in quantum mechanics. And it's very mysterious, collapse of the wave function. Before you saw it was in a superposition. Afterward, it's one or the other, and that's what it's going to be from now on. You have come very close to inventing what is called the many worlds interpretation of quantum mechanics, which says that
Thank you very much.
When you're late.
I can't text my mum.
Yeah.
She'd be very proud.
About 100 years too late.
Yeah, a little bit too late. And the guy who invented it sort of went crazy. But Hugh Everett, who invented the many worlds interpretation, said, look, when you talk about these experiments, you have to realize that you, a human being, are made of quantum mechanical particles. You obey the rules of quantum mechanics. You have a quantum state that can be in a superposition. When you open the box and look to see if the ball is red or blue, it's not that you see it red and the blueness disappears, or vice versa. It's that you evolve into a superposition of the ball was red and you saw it red, plus the ball was blue and you saw it blue. And there are now two different copies of the world in which you saw different things going on. They're both equally real, and they will never communicate with each other ever again. They are, for all intents and purposes, separate worlds, multiple worlds in reality. And if you believe that, which I do, actually, I think it's probably true, you should go to the App Store and download something called Universe Splitter. It is an iPhone app where it gives you two options, and you can say, okay, I would like to study physics in graduate school or study philosophy in graduate school. And it will send a signal to a lab that sends a photon and splits it and then observes it, and it comes back and tells you which branch of the wave function of the universe you're in, and you should go study philosophy. And if you promise to do what the phone tells you to do, there's another branch of reality in which you became a physicist.
And when do I go on the X Factor with that?
That's right.
Thank you.
One more question, good, right in the middle right there. You can just move it right there.
I read earlier this year that Stephen Hawking, I think probably in connection with the firewall issue, was saying something about maybe black holes didn't exist as such as having an event horizon and maybe had more of an apparent horizon instead. Can you sort of say a bit about that, sort of explain it a bit and sort of how it adds to the debate?
Well, I can say something as a science writer that the news coverage was terrible of that. That's actually not what he said. And the headlines and some of the coverage of that was not very good. I think really hadn't looked really deeply into what Hawking was actually saying. If you ask Sean will tell you that he thinks Hawking is, possibly not correct. I will let you elaborate.
It's one of the few times in my life that I've thought to myself, poor Stephen Hawking, because he wrote this paper, and it was really just a conference proceedings. He'd given a talk, and he typed it up in his computer, and he sent it off. And it was very short. There were no details, no equations. It was just like a suggestion. But because his name is Stephen Hawking, and he's done amazingly wonderful things in the history of physics, and everyone pays attention to him, people latched on to it. And there's this one sentence in his paper which says that, therefore, black holes do not exist in the sense that blah, blah, blah. Instead, they exist in this sense. And the headline in Nature the next day was Stephen Hawking thinks that black holes do not exist. So if you go back to the picture Jennifer showed of the center of our galaxy, remember, this is data. The orbits of these stars that are plotted here, it's done in a computer program, but they're based on observations of the stars around a big plus sign, which we believe is a black hole because it's enormously massive and enormously small and enormously dark. And Stephen Hawking, if you asked him, is there a black hole at the center of our galaxy, he would say yes. So I think that he's gesturing in the direction of a certain kind of resolution of the black hole firewalls problem to take the idea of an event horizon a little bit less seriously, given that black holes eventually evaporate. But there's a long way to go before enough meat is put on those bones to call it even a proposal, much less a theory. And I think I'm being told that we are out of space and time, so we will have come to the end of space-time. Thank you once again all for coming.